Hello my dear students, this is Akash SD. Hope so doing good. Today we are going to learn Gauss law and its applications based on the electric flux. Okay, so students, let's start the class. So first thing is here the Gauss law here. So you know very well about the Gauss law, but still we will see the definition. So here please, according to this law, the net electric flux through any closed surface is equal to the net charge enclosed by the closed surface divided by epsilon naught, and this closed surface is called which surface? Gaussian surface also. Okay students, so mathematically we are going to learn here, but first here I have taken one surface is there, symmetrical surface is there, and let's, in case here some charges are there, I have taken like this. Now let's take charge q1, charge q2, charge minus q3, charge q4, outside charge q5, and here even I have taken charge q6. So what will happen that here electric flux, which electric field? Net electric flux. Okay, so this net electric flux, what will happen? This phi E will be equal to which surface? Closed surface E dot ds. Okay, and this one is what is charge enclosed, that means q enclosed by epsilon naught. This is according to the Gauss law. And we know very well what is the value of this charge enclosed. This charge enclosed, as the name itself is telling, enclosed charge. That means which charges are enclosed? We can write here q1 plus q2 minus q3 plus q4. Now this is the meaning of this enclosed charge here. Okay. After the student, some important point is there. Let's see here what is the point. This law is suitable for a symmetrical charge distribution and valid for all vector fields. Obeying which law? They should obey the inverse square law. Inverse square law, na? Like electric field is there due to the point charge k into q by r square. So there also this Gauss law will be valid. Okay, remember that. Next one, students, we are going to see the proof also. Na? Proof how this Gauss law comes here. Na? So here please, here I have taken one Gaussian surface I have taken, and here one charge q is there at the center. Okay. And let's take this distance is how much? This distance is small r. Now what I will do here, I will take a very small area. Now this area, how much I have taken here? ds. And you know very well, due to the point charge, electric field will in which direction here? Outward. So this is the direction of the electric field. And after that, area vector in which direction? As this is the which surface? Closed surface. That means area vector is also which direction? Outside. ds. Now, and here angle between electric field and area vector, how much here? 0 degree, because both are in which direction? Outward direction. So students, the small electric flux through a small area of closed surface is given by, see place here, d phi e. Now very small. This is given by what here? We can write here vector e dot ds, or we can write here e ds cos 0, and the cos 0 value is 1, so we can write here e ds. Now net electric flux through the closed surface. Now we are going to see overall. So overall what will happen that here, let's see here please, here this phi e will be what here? Closed integration of d phi e. Okay, kindly put the value of d phi e, how much there? E into ds. Now students, you know very well, each and every point on the Gaussian surface is equidistant from the charge. That means what will happen? The electric field will be constant, so it is the constant coming outside, and here integration of the ds here. Electric field value due to the point charge, we know very well what is the formula? 1 by 4 pi epsilon naught into q by r square. And if we take overall surface, what will happen? The area, students, it will come 4 pi r square. So what will happen? This 4 pi cancel, and even you can see this r square and r square is also cancelled. That means what it will come here? Q by epsilon naught. And have to remember that one thing, as r square and r square is cancelled, that means this law is valid for independent of whatever is the shape of the area, shape or even the size also. You are getting what I am telling? The size means even this radius is r, even the radius is 2r, even the radius is 3r, answer is going to be the same only. Okay, please remember that very well. Next students, we are going to see this one, important points regarding the Gauss's law. So see here please, first one, flux through Gaussian surface is independent, as I told you, independent of its shape or size. So here please, here I have taken students, let's take here I have taken charge q. Now so in this situation, flux will be how much here? Flux will be anyhow q by epsilon naught. Now even you keep the charge here q, how much flux is? Same q by epsilon naught here. Even this charge can be anywhere inside. Let's take for example here I put charge q naught. In this situation also what will happen? The flux will be same only. Okay, and let's take for example this radius is a and this radius is even 2a. So even what is happening? The shape of the Gaussian surface is changing, size is changing, but what will happen? The answer is going to be the what? Answer is going to be the same answer only. Okay. Next one, students, see please. Electric flux through Gaussian surface depends only on the charges present inside, as I have told you very well, like here charge Q1, here charge Q2, and even charge outside minus Q3, for example. So which kind of enclosed charge we have to take here? As it is Q1, Q2, only this one. Outside charge does not matter here. Now only inner charges are there. After that, next one, students, see please. Electric field intensity at the Gaussian surface is due to all the charges present inside as well as outside. Okay. So see here I have taken how many charges? 3 charges are there. And if I take here any point here, let's take I have taken point A. So what will happen that at point A, electric field due to which charges? Electric field due to 3 charges here. So if I am writing here, see at point A, which electric fields are included? Here we can tell here all, due to all, E1 plus E2 plus E3. Okay, because this thing will be used here. Now closed integration. If I write here EA dot ds and here charge enclosed by epsilon naught. So as I told you, this electric field is due to all the charges. But this enclosed charge is which one? Only Q1 plus Q2. Outside charge does not matter. Okay, students? Great. Great. Now, students, let's see. We are going to see the cases of the electric flux here. First case, see please. When an electric dipole is enclosed by the Gaussian surface. And you know very well what about the electric dipole. Electric dipole means here minus Q, here plus Q. Net charge how much? Net charge 0. So here, students, you can see the enclosed charge means minus Q plus Q how much? 0. That means in this situation flux will be how much? 0. Very easy. Okay, sum of the charges, even dipole or any charges are there, if the sum is 0, flux is going to be the 0 here. Now next one is, students, case 2, when a charge Q is placed at the center of an imaginary hemispherical surface. Now so here you can see one hemispherical surface is there, and here I put one charge Q at the center. So here what will happen, that students, if in case I draw one symmetrical surface here like this, you see. Now we have to just draw the symmetrical, because Gauss law is applicable for the which kind of surfaces? Symmetrical situation. The things will become easy. So you can see very well here one complete sphere is there. So we can tell that here, students, due to sphere how much flux will be there? Q by epsilon naught. But this sphere is made up of how many hemispheres? 2 hemispheres. That means we can tell due to 2 hemispheres flux how much? Q by epsilon naught. Hence due to one hemisphere flux will be how much, students? Again Q by 2 epsilon naught by the symmetry here. Okay, good. Next one, students, see please, just like a same scenario. See here, when a charge Q is placed at a distance a by 2, and the edge, this cube is there, this square is there, its a side how much? A. That means if we draw here one imaginary cube, what I'm telling, students, if I'm drawing here one imaginary cube here, let's take here, I'm drawing here one imaginary cube. Okay, one imaginary cube I'm drawing here like this. So you can see very well, students, in this situation, now this is a one imaginary cube. Okay, and this charge should come where? This charge is at the center here, somewhere here at the center coming here. Okay, a by 2, because this length is a by 2 and this is a, this is a, this is a, all this a. That means charge is coming where? At the center. Again I'm drawing here like this. Kindly see it very well. Like this. The charge will come here at the center. So in this situation, you know very well, students, what will happen that here one cube is made up of how many surfaces? 6 surfaces. Yes or no? That means we can tell that here through the 6 surfaces. Flux how much? Q by epsilon naught. But in our situation, how many surfaces is there? Only one surface is there. That means due to one surface, flux will be how much? Q by 6 epsilon naught. And remember that this here, if the side is A, the charge should be at a distance of A by 2. Then only after symmetry drawing, the charge will come at the center of the cube. Okay, please remember that. Next one, students, see please, case 4. When charge Q is placed at the center of face of one of the faces of a cube here. Okay, students, so here you know that in a cube how many faces? 6 faces are there. But here I have taken one face like this here. Okay, one face. And charge is where? The charge is at the center here. Is it? So students, what will happen that here again we have to draw one symmetry. So here please, if I draw here like this, like this, I have drawn here. You can see here, students. like this. Now I have given here. Now you can see that here the charges came at the center here. Now you can see how many cubes are there? 2 cubes are there. That means we can see here, in a given situation, 1 cube was there, but by the symmetry I have drawn how many cubes here? 2 cubes. So you are here, please. Due to 2 cube, flux how much? Q by epsilon naught. And in according to our situation, how many cube is there? 1 cube is there. That means how much it will come here? Q by 2 epsilon naught. Here, very easy. Next one, students, see please. Case 5. When charge Q is placed at the center of an edge of one of the edges of a cube, at the center of an edge of one of the edges of cube. Let's take for example here. Here we have put. This is we have put here. Is it like this? So students, when you will think about here, we have put at the center of the edge. So what will happen that here like this? If you imagine how many cubes we can draw here, we can draw here the 1 cube. 1 cube is here, 1 cube is backside. Then after that, 2 cubes about that. That means total how many cubes will be there? 4 cubes will be there, and the charge will come at the center. That means through the 4 cubes. How much flux? Q by epsilon naught. Hence, due to 1 cube, how much flux will be there? Q by 4 epsilon naught. Very easy. We have to draw the 4 cubes so that the charge should come at the center, and we can apply the symmetrical situation. Next one is, students, see please, case 6. Here, when charge Q is placed at the corner of one of the corners of a cube is there. Okay, students. So again, I am telling here. Let's take for example. Now I have kept the charge here, charge Q. So in this situation, we have to calculate how much flux associated with the cube. First, we are going to go through the cube. So students, again, if you see the symmetry, think please how many cubes we have to draw so that the charge should come at the center. 8 cubes we have to draw. Think please here. 1 this side, left, right. 2 backside and 4 cubes above that. Then only the charge will come at the center of 8 cubes. Okay, that means here we can tell due to 8 cubes, how much? Q by epsilon naught. Hence 1 cube. How much it will come here? Q by 8 epsilon naught. Okay, after that, sometimes question used to come from here also. Flux through each of the faces of the cube. This situation. So here what will happen that here, students, here 6 surfaces are there, is it? But here please, if you think about this charge Q, so this edge is made up of how many? Intersection of how many faces? 3 faces. So this one I have drawn yellow color. This also I have drawn yellow color, is it? And what will happen? Backside also. Backside, let me take here this backside. This backside, this cube I'm talking about here. So what will happen that here, electric field lines will be parallel to these 3 surfaces. That means what will happen that here, through these 3 surfaces, this yellow, this upward yellow, and one backside yellow, is it? So due to these 3 surfaces, I'm giving the name here, phi 1, phi 2, phi 3. Flux will be how much here? 0, because electric field lines will parallel to the surface, they will not cut the surface. After the students here, 3 surfaces went. Now, how many surfaces left? 3 surfaces are left. Okay. So, we can tell here like this here. Now, 1 cube we have seen Q by 8 epsilon naught. But this 1 cube, how many surfaces left? 3 surfaces left. So, we can tell here 3 surfaces. How much flux is there? Q by 8 epsilon naught. That means hence due to one surface, how much? Q by 24 epsilon naught. And like that, how many surfaces are there? 3 surfaces are there. That means we can tell that here phi 4, phi 5, phi 6, how much? Q by 24 epsilon naught. Now due to 3 surfaces 0, and due to the 3 surfaces Q by 24 epsilon naught, and the total flux how much? Q by 8 epsilon naught.